So, we are discussing about the electronic structure of molecule. Or basically electronic spectra. Okay. So, what we have seen this I will just show you here. So, here this we have seen that any molecules show this electronic structure, electronic spectra, although some of the molecules which are not having permanent dipole moment, so they do not show the rotational spectra as well as vibrational spectra, that is microwave spectra or this infrared spectra. But in case of electronic spectra, so this all molecules which shows the rotational or vibrational spectra, they also shows this electronic spectra as well as they these other molecules like CCl4, carbon dioxide, hydrogen molecule, oxygen molecule, chlorine, iodine. So, they also shows the electronic spectra, although they do not show any pure rotational or vibrational spectra. Okay. So, this in electronic spectra basically it has coarse structure as well as fine structure. So, coarse structure it is related with the vibration of the molecules, and fine structure it is related with the rotation of the molecules. So, if we consider just one electronic state, and in that electronic states there are vibrational energy level. So, this black one here, this is the electronic state, and this next black one. So, this is the another electronic state, excited state may be. So, this difference is 10 to the power 5 centimeter inverse, and now with each electronic state there are vibrational state. So, these green lines. Okay. So, this I have written here this V dash vibrational quantum number. So, this V dash equal to 0, 1, 2, 3. Okay. So, this is the lowest energy state, electronic energy state, and in that state these are vibrational energy level. So, similarly for higher electronic state, so there this vibrational energy level is V double dash 0, 1, 2, 3, these are associated with it. Now, each vibrational level again it has fine structure, means rotational, due to rotation there are again finer energy levels. So, I have drawn here with red line. Okay. So, now if we just neglect the fine structure for the time being, if we just consider the vibrational structure. So, that is called basically coarse vibrational structure, electronic structure. So, in that case, so here this selection rules it is del V equal to 0, plus minus 1, plus minus 2, etc. It is all are allowed, all transitions are allowed. So, now two types of spectra, coarse vibrational electronic spectra is observed. So, one is called progression, another is called sequence. So, for progression this where here we have shown this del V equal to 0. So, here to here this transition, del V equal to 1. So, here to next vibrational level. Okay. So, similarly 2 from V dash equal to 0 to V dash V double dash equal to 2. So, this is the progression. Similarly, this another sets we have shown here del V equal to -2, -1, 0, 1. So, this transition. So, this is also called progression. Other one is called sequence. So, maintaining this del V equal to 1 or del V equal to 0. So, this is del V equal to 0. For this, these are the transition that all are follows that del V equal to 0. So, this type of spectra is called sequence. Similarly, del V equal to 1 another sets of spectra. So, these are the example of progression and sequence. Okay. Now, if we if we consider the progression, so there basically this transition between the vibration energy levels associated with different electronic level. So, E dash, E double dash, similarly here vibration V dash and V double dash. So, in case of progression, so this transition and these lines are basically it is called by this label V dash V double dash. So, transition from V double dash 0 to V dash 0. So, it is 0 line, similarly 0 line, similarly here 0 to 1. So, V dash is 1, V double dash is 0. So, 10 line, 20 line, 30 line. So, these are the these transitions are labeled with V dash V double dash. Okay. So, what are the wave number for this each energy level? So, that one can find out just E total, that is E electronics plus vibration energy level. Okay. So, E electronics and then vibration energy levels for different value of V vibration quantum number V equal to 0, 1, 2, 3 etc. Okay. So, now transition from one electronic state to another electronic state, and then one electronic state where this molecule is in a particular vibrational level, and then it is going to the another electronic state, but different vibrational level, okay, at different vibrational level. So, what will be the energy or wave number of these spectral lines? So, that one can calculate. So, this wave number of the spectral lines will be energy difference of the electronic state E dash minus E double dash plus, now here from V dash to V double dash. So, here this vibration energy, so that from electronic state E dash. So, if that is V dash is the vibrational quantum number. So, this energy minus that the V double dash in that vibrational level, whatever the energy. So, if you just take the difference of these two, as well as here already we have taken electron difference in electronic state. So, this will be the wave number of the spectral lines, and basically in spectroscopy one can see this type of coarse vibrational coarse structure in electronic spectra, and one can measure the wavelength or wave number of this frequency from spectroscopy for each lines. Okay. And then basically one can determine the frequency, this omega E dash, omega E double dash for ground state as well as excited state, anharmonicity constant x e dash x e double dash as well as this electronic energy difference also can be calculated using this expression. Okay. So, now question is here whatever the spectral lines I am showing, and here you can see these spectral lines, basically their separation are decreasing with higher quantum number, vibrational quantum number. This is one observation, and second observation is that intensity of all lines are not same. Okay. So, now we will concentrate this why the intensity are not same for all lines. So, why it is different and how it varies. So, that we would like to see, and that is basically intensity of vibrational electronic spectra. So, that is as already I have mentioned that Frank-Condon principle generally tells about the intensity of vibrational electronic spectra. So, what is that Frank-Condon principle? It is telling that an electronic transition takes place so rapidly that a vibrating molecule does not change its internuclear distance appreciably during the transition. So, actually this molecule is all the time this if it is diatomic molecule. So, these two atoms are vibrating and they are in different vibrational energy level. Now, they are in different vibrational level means their separation are different. Okay. So, with time their separation changes. Now, during the transition from one electronic state to the another electronic state, so this transition is so rapid that this during the transition one can assume or consider that the molecular atomic separation internuclear distance will not change during this transition. Okay. So, that is the Frank-Condon principle. So, now from this, to understand this principle, basically one has to understand that it is telling that this transition actually can be represented by the vertical lines. So, what is the meaning of that? So, that I will tell, but here let us understand that the probability distribution for a diatomic molecule according to quantum theory. Okay. Probability distribution for a diatomic molecule. So, harmonic oscillator, in case of harmonic oscillator you know that this is the variation of the potential energy. Okay. This is the Morse potential curve, Now, it has different states, different energy levels. Okay. Now, what is the probability of finding molecules in different states? And so that depends on basically. So, this curve has come, how it is, it has come, that I have discussed. So, one can consider this one atom is fixed here. Okay. Now, another atom is vibrating, So, depending on the distance of the another atom, so they are in different energy levels. Okay. So, now what is the probability of finding the molecules in here? So, here it is shown that this probability from quantum mechanics, this at ground state, okay, this probability of finding particle, its the probability curve is like this. Okay, chi square, basically it is like this for V equal to 2 first excited state. So, probability is like this, second probability like this. So, from here one can see that the probability is shifting towards the at the end of the curve, okay, when we are going towards the higher vibrational quantum number. Okay. So, for lower quantum number, so its probability is in middle, V equal to 0, it is highest probability is here. Now, this probability is shifted, is going towards the end of this vibrational curve. So, end of this vibrational curve, what does it mean? There basically is the turning point of the oscillator. So, in classical mechanics also tells that the oscillating particle spend more time at the turning point. Okay. So, one atom is fixed here and another atom is this is the equilibrium position. Now, it is vibrating. Now, this is the turning point, it is going and during turning point. So, more time spending at the end, at the turning point, more time spending at the turning point. So, that means at the turning point means here at the end of this curve, okay, near the curve. So, the probability will be maximum. So, classically as well as quantum mechanically we can say this is the probability distribution of the molecules, or to find out the molecules, this is the probability distribution. Now, during in each vibrational state the internuclear distance are different, right. So, in each vibrational state the internuclear distance are different. Okay. Now, during electronic transition the internuclear distance does not change. Okay. That is what Frank-Condon principle. Okay. So, the transition can be connected by a vertical line between the two vibrational state. Okay. So, basically that if we consider, this molecule, it is in a particular state, vibrational state. Now, during electronic transition, so this molecule may be in another vibrational state or it can be in same vibrational state. Okay. So, if we consider this curve for one electronic state and corresponding vibrational state, and if we take similar another curve, and there if we show the different vibrational level. Okay. So, during electronic transition they are not changing the interatomic distance. Okay. So, that means this is for one, another if we consider. So, now the distance are not changing if we consider that one. So, considering they are in the same configuration. So, we can just draw vertical lines to show the transition. So, in that case one has to consider that in ground state where is the maximum probability. So, it is going to the next excited state, there it will go in that state where the probability is maximum. Okay. So, in space basically here itself, considering the connecting the maximum probability of this lower electronic state to the higher electronic state means their corresponding vibrational states. At lower electronic state there are vibrational level, it was in a particular vibrational level. Now, it is excited state, electronic state, now their vibrational levels are there. So, in which vibrational level it will go, so that we can connect with the vertical line basically connecting the maximum probability of this vibrational level of this ground state and the excited state. So, that's what the meaning of this Frank-Condon principle, and that I will show you. So, here we have considered this 4 configuration. So, here this is one electronic state and their corresponding vibrational states, and this is another excited state, electronic state, and their corresponding vibration state. Now, during electronic transition, as this vibrational there will not be change of electronic this internuclear distance. So, if we consider, okay, this was the position of this vibrational state at lower electronic state and the higher electronic state. So, now this and we are considering that this molecules are at the ground state, ground vibrational state. So, this here V double dash equal to 0. Now, from here if I draw a vertical lines, so here we have to see here the where it will cut. So, it will cut, we have to draw, we have to choose this vertical line in such a way that it will connect the maximum probability of the molecules in that vibrational level. Okay. So, here it is in the middle, maximum probability. Now, from middle if I draw a vertical line, so now it is going to the middle of this vibrational level. Okay. So, there V dash equal to 0. So, this will be the possible transition, maximum possibility between of this transition for this configuration of the vibrational states. Okay. So, this is the called 0 transition. Okay. Now, in this case this 0 that is the maximum probability of transition. So, that is intensity of these lines will be maximum, and then this from 0 to 1, you see if I draw these lines here. So, I have shown the probability of this here, you can see this probability, if I draw this way, this probability at the middle is really small. Okay. So, because it is shifted towards the end. So, but there are some probabilities. So, you will get spectral lines, but intensity will decrease. So, intensity will decrease for 1 0 and then further decrease for 2 0, etc. Okay. So, in this case, in this configuration, one will get the distribution of the intensity like this. So, here 0 line will be the will have the maximum intensity. Similarly, if this is the situation during electronic transition, okay, so this ground electronic state and this excited electronic state, during this electronic transition, this was the configuration of the vibrational state. Okay. So, we considered that there will not be any change in vibrational in atomic nuclear distance, okay, internuclear distance. So, here now starting from the 0, if we draw the vertical lines, so it is going, it is cutting this at this V dash equal to 2. Okay. So, this is the maximum probability, and here the maximum probability at V equal to 2. So, this basically will have the maximum probability of transition. So, 2 0 lines will have the maximum intensity. 2 0 lines will have the maximum intensity, 1 0 will be the lower, 0 0 will be the even lower. Okay. So, here 0 0 was the maximum probability. Okay. So, intensity was the maximum, and now here 2 0 will be the maximum intensity. Okay. So, here we have shown here also in this case also, if this is the configuration of vibrational states, okay, in ground electronic state and the higher electronic state. So, there if transition occurs in this condition situation, so you will get also this 2 0 highest intensity. Okay. Now, this is extreme case if their vibrational state is like this. So, here only this transition probability will be maximum here. So, this basically I think this is the very high V dash value, vibrational quantum number V dash, this is a high V dash value, and this basically it is close to the continuum. So, after that, so all the whatever you will get is a continuum line you will get, because separation between the vibrational energy levels at higher V, you know, it's a very tends to 0. Okay. So, the spectral lines that whatever we will get, so that's it will basically the continuum spectra, and their continuum spectra intensity here it is maximum, and then it's for other transition it's just decay, and for other transition close to this continuum lines, or where maximum intensity we observe. So, other few lines you may get, but they will have the reduced intensity. Okay. So, this is the way one use the Frank-Condon principle to explain the distribution of the intensity of the spectral lines, basically vibrational spectral lines. So, that is the core structure, vibrational core structure of the electronic spectra. So, one has to really try to understand this Frank-Condon principle, and I think I tried to explain, but you should think over it and try to be clear of this principle, because it is not very tough, but it's one has to realize, and I think one has to understand the probability of the molecules staying in different vibrational states. So, this from quantum mechanically we have shown that probability is at the close to the curve at different higher, basically higher vibrational states. This probability is maximum at the close to the curve, and that is nothing but the turning point. So, classically one can think that at the turning point the probability of the molecules in the vibrational level is maximum, because it takes more time to turn. Okay. So, more time it will spend there. Okay. So, I think I will stop here. I will continue in next class. Thank you.